Hello learners, so in this particular session we will discuss about two famous searching techniques. There are two famous searching techniques. First is depth first search and the another one is breadth first search. So in the first session we will study in detail about depth first search and discuss the algorithm. With it we will also discuss some examples. Moving on forward now, searching in breadth first search or depth first search means that you have to explore a graph. Okay, so you will be given a graph and you have to traverse through the nodes of graph. Nodes means vertices, every vertex of a graph in a specified manner. Okay, so the specified manner will be discussed by something will be initiated by something called either depth first algorithm or breadth first algorithm. So the searching basically depends upon the data structure both are using. So depth first search is using a stack data structure, whereas the breadth first search is using a queue data structure. Okay, so you already know what a stack and queue is. So stack and queue are two different data structure that will be used. Now you can remember it like depth first search. So stack is in the form of a depth, like you will place one element, then another element, upward another element and another element, and if you want to pop the stack, you just delete the first element that is at the top of the stack. So you seeing that there is, when you are putting on element in the stack, so there is a depth in the stack. Now depth first search using a stack data structure. Now breadth first search is like if you look at the breadth of anything, so it will be arranged in a queue format. So the breadth first search will be using something called first in first out, and the depth first search will be using last in first out. The last element which is entered in the stack will be the first element which have to go, but in the breadth first search, the first element which enter in the queue is the first element that have to go. Like you're standing in a queue in front of a bus station and you are there for a ticket, and if there is a long queue, the first person on the queue will be the first person to get the ticket and get out of the queue. Similarly, the searching is solely based upon which particular data structures are using. So if you're using stack data structure, then depth first search. If you're using queue data structure, then breadth first search. Okay, so there are also many other applications in graph search of depth first search. In this section we will illustrate about how depth first algorithm works and proceed further by discussing various example. Okay, so the logic behind the depth first search is to go as far as possible from a given starting point, or you can in the in form of graph you can say, instead of point you can say node or a vertex, searching for the target. Okay, so it means that you have to decide which target it is and then you have to apply the depth first search and you have to go there. In case we get a node that has no adjacent or successor node, we get back recursively and continue with the last vertex that is still not visited. So what will happen there, that depth first search, how it will work, firstly it will have some starting point. After the starting point, you have to add the vertices that are adjacent to this starting point, and whenever you reach certain vertex which has no adjacent node that is not already being explored, then you have to just close the stack and get back to the calling node. So I'll show you, because it is going on recursively, the call will be placed recursively, and then when a particular when you need to reach at a particular node where vertex is there and it has no adjacent vertex that is not already being explored, then you have to close the record and have to go back. Okay, so broadly you can divide it into three steps. First is you have to take the vertex that is not visited yet and mark it as visited. Then the second step is that you have to go to the first adjacent non-visited node. Okay, keep that in mind. When you have visited first node, the adjacent node of those vertex of this vertex which you have visited will be put it onto the stack, and you have to take a look at which particular node is not visited yet, and then you have to visit that node and again mark it visited. Now in the last step, that if all the adjacent vertices like successors of the considered vertex is already visited, then it does not have any more adjacent vertex, then you go back to its parent vertex or parent node. Okay, so just before starting the algorithm, there is some terminology that will be used in the algorithm. The first terminology that it will be using is something called a vertex. Another terminology is that if a particular vertex is visited, you will say it is visited, and if it is not visited, it will be written as not visited, or visited equal to 1 if it is visited, and visited equal to 0 if it is not visited. Another is that there is some color scheme that is being also used here. So if the color of the graph is white, it means that it is not visited. So what it means is that visited equal to 0 yet. Now another color scheme that is being used in the graphs is gray. So for a visited node, so if you have visited the node one time, you will color that particular vertex as gray. Another is black. Black means that your stack is being recursive call is being placed. It means there is no other vertex, adjacent vertex that is left to visit, and you go back to the parent node. So then you mark this particular node as black. So I'll show you in the example what it means is that. Another thing is that there is two timestamp will be used in the algorithm. First is called TU. So TU means that first time discovering visiting a vertex, it stores a counter or a number of times. FU. Now FU means that finish end of and target vertex whenever you reach. So this is it. Now let's try to write the DFS algorithm. Let's try to see what is a DFS algorithm. Keep that in mind. In the algorithm, V stands for vertex set, E stands for edge set, because this is the normal terminology of graph. G equal to V comma E, where G is the graph and V is a vertex and E is the edge. And adjacency list for a given graph G is sorted in an adjacent array. As described, we have already discussed it. So I'll show you that what it means is that you will place everything in an array, and this array we will calling beta stack. Okay, so color any array color will have the status. So every color, like 3 colors we have already seen in the terminology, that white, gray and black, it will tell you about the status of a particular vertex. Okay, moving on forward, this is the algorithm. It is again divided into 2 parts. The first part is the DFS and one argument G. Another part is the main part, that where you have to visit the node one by one recursively. That is referred to as DFS visit. Okay, so what will happen in the DFS graph? Firstly, you have to check the loop will be for every vertex. So V, for each V in vertex set, the loop will be run for V plus 1 times. How many vertexes are there? If there are 5 vertex, the loop will be run for 6 times 5 plus 1. Then in the starting, the color will be white. So keep the color white as it is. And then P of V equal to null, means parent of the first node will be null because you haven't visited anything yet. Time is again not, any operation is not been done till now. So time is again constant time will be there. Now for each u in V, now you start visiting the node one by one by calling the function DFS. So you have seen the vertex set, now you try to visit one. Now if the color of u is equal to white, so you have to visit the first node once, and always the first node color will be white because it is not visited yet. Now if it is white, you will call the DFS visit procedure. Like if you have seen in the merge sort, the heart of the algorithm is merge procedure. The similar way here in the DFS, the heart of the algorithm is DFS visit. So everything will happen on DFS visit. Every call, recursive call will be placed in DFS visit. Now check, it is calling if the current node is white, it will call a DFS visit U. So it will, whatever the node is, suppose the node is named as A, so it will call DFS visit A. So A will be the node that is being called. Okay. So now what you do, first step is you because you have visited this node, first you will visit the node, you will color it as gray. Now it will take constant time. Then you will add the time, whatever time it was taking. Now in the next step you have to add the adjacent nodes. Adjacent means every node which is connected to this gray node that you have colored right now. Like if you have white node, that is 1. Now when you go into the DFS visit, what you will do, you will color it as gray. Then you will add the adjacent nodes of this color of this vertex 1 in the array. Okay. So most of it, because it is the adjacent nodes are not being visited yet, so the color of these nodes will be again white. Now it means these are unvisited, you have to visit it one by one. Now everything which is placed in the stack, you have to do it one by one. Okay. So now when your adjacent node is being added to the array, you have to check if the color is white. Yes, the color will be white for the first time. Then you have to set the parent of this. So suppose the parent 1 node is already being colored as gray. So the adjacent node to 1 is 2 and 3. So you will add 2 and 3 to the array. Now the parent of 2 will become 1. Okay, because by the help of 1 you have added 2 and 3. Okay. So now again P of V, the parent of the unvisited node will become the calling node. Now if it is 1, it will become 1 here. Again a DFS visit call is being placed. So this is called a recursive call. It is calling the function again and again, and it will go on further again and again and again till all the nodes, adjacent nodes are being visited. And in the end, if all the nodes are visited, you have to make it black. Okay. So I'll show you one by one with the example that what do I mean by this. So check, this is the example given here. In this example you can see that there are 1, 2, 3, 4, 5 nodes, and the name of the node is 1, 2, 3, 4, 5. Okay. So if you want to draw a adjacency list of this particular example graph, you can simply do it like shown in the slide, that 1 is being connected to 2 and 3. So this 2 and 3 will be called as a adjacent node. Okay, so this is what a adjacent node is. So it is directly connected to these nodes. So you can add in the adjacency list. Okay, so 1 is being connected 2 and 3. So 2 and 3 is added to the list. Now 2 is connected to 1, 3 and 4 and 5. So you will directly add 1, 3, 4 and 5. Similarly check for 3. 3 is being connected to 1, 2 and 4. So it will be added to it. Now 4 is being connected to 2, 3 and 5 is being connected to 2 and 4. So if you want to draw adjacency list of it, you can simply draw the adjacency list in the starting as shown in the example. Now we'll go with the depth first part. Okay. So first part of the algorithm will be that the first node 1, that is referred to as 1, initially it will be white. Okay, it means that this particular node is not visited. Now when it is visited with the call of DFS visit procedure, now you will pass DFS visit, in the argument it will be 1, the name of the vertex. Now when it is called given to the DFS visit function, the first step will be, it will mark it as gray. Now what it means is that, it means that the one node is being visited. Now the next step is that you have to add the adjacent nodes that are adjacent to 1. Okay, So the adjacent nodes are that are directly connected to 1 is 2 and 3. 4 is not directly connected because there is no line between 1 and 4, so you cannot call this is adjacent. Now the parent of 2, now you will explore each and every adjacent node one by one. So what will be the parent of 2? The parent of 2 will be the calling node, which will be 1. Okay, so I'm just setting the parent of 2 as 1 so that you remember who calls which particular node, because at the end when there is no adjacent node, you have to return to the calling function. Okay, because recursion will be in the form of an activation record. Okay, so if you are done with because there is a recursion going on, the function will call itself again and again. So whenever a function call itself again, it will again get into another activation record. So in the end, when there is no node left to visit, it have to complete the activation record, have to go back to the calling function. So that is why we are also keeping the record of the parent, so that we know that this particular parent, this particular node is being called by this parent. Okay, so now second, the parent of 2 is 1. Now we'll go, you can visit 3 as well, first 3, or you can visit first 2 as well, because both have equal priority and both are adjacent to 1. So whichever one node you prefer, you can visit. Okay, so I am just going with the 2 here. So I'll again place a call to DFS visit 2. Now what will happen, the first step will be DFS visit function will be called. Next it will be marked as gray. Next step will be, we'll write the adjacent nodes to 2. Okay, so what are the adjacent node? Actually it is 1, 3 and 4, but I have not added 1 because it is already being explored. So I'm only writing those particular nodes here which are not visited yet. So those are those who are white. Okay, so I've written the adjacent node here as 3 and 4. So now what is the parent of 3 is 2. Now keep a record that because the adjacent node is 3, the white, it is also white. So you have to explore the 3 node first, and you have to keep a record of the parent of 3. So I've kept the record, that is 2, and I've again called the function DFS visit 3. Okay, so now again the next part will be when you have called the DFS visit. First thing is that you will mark it as gray. So keep in mind that anything is not marked black yet. Okay, I'll show you when it will be marked black, when the activation record is being closed. Okay, so first you have marked it as gray. Now what is the next step? Next step is that you have to add the adjacent nodes here. So adjacent node which is not yet explored is 4. Okay, so I have added 2 here, just ignore that part. But the adjacent node that is not being visited yet is 4. Now again, what is the parent of the 4, which is 3, to keep a record that the next node which will be called, the parent is 3. Now again the calling will be DFS visit 4 now. Now when you visit DFS visit 4, the first step again will be that you have to mark it as gray. After it is marked as gray, what you have to do is that you have to again mark the adjacent edges. Now what is the adjacent vertex to 4 which is not yet visited, which is 5. So ignore the 2 here that is being written here. So 2 is already being visited, so you can just ignore that 2, just written the adjacent vertices in this graph. Now the parent of 5 is 4, again the calling function is 4 for the node 5. Now again the last part is that you have to visit 5. Now the first step is that you have to put it as gray, and then what are the adjacent edges to 5, which is 4 and 2. Now keep that in mind, these 2 particular vertices is already being visited. So what it means is that you have reached a point where no adjacent edge that you have found is not visited. Now at this point, every adjacent edge is visited. 4 is visited as well as 2 is visited. It means you cannot explore further. So what it means is that you have to go back to the calling function. So it means the record is being closed and you have to go back to the calling function. So what it means, you have to mark the 5 node as black and you will return to the parent of 5. Now what is the parent of 5? The calling function. Who have called 5? Check in the back. 5 is called by the parent, that is 4. So you visit, again DFS visit 4 will be called. Now check for it, it is already marked as gray. So don't do that. There is no need to mark it as gray. Now check for the adjacent edges. Adjacent edges is 5 and 2, which is already being visited. So what you have to do, you have to again mark the 4 as black and go back to the calling function. So who have called 4? So 4 is called by 3. So that is why we are keeping the record of the parent you have seen in the algorithm. So again when you do it with 3, now what are the adjacent edges to 3? 2 and 4. Okay. So again 1, 2, 4, they are all again already visited. So you cannot do much. What you have to do, you have to mark it as black. So what is this happening is that we are closing the activation records by going back to the calling functions. Okay. So now mark it black, again go back, who is calling, who has called 3, who is the parent of 3 is the calling function of 3. So 3 is called by 2, again you will write DFS visit on 2, again the adjacent nodes are already being visited, so you will mark 2 as black. Similarly, in the end you will get back to 1 and again all the adjacent nodes to 1 is already being visited, so you will mark and close the activation record and close the stack of 1. So this is how the DFS algorithm works. Okay, so now every particular vertex is marked as black. Now the whole algorithm and the whole procedure is being complete. Okay, so now what is the visit pattern? So which particular node or which particular vertex is visited first? You can check. First 1 is visited, then 2 is visited, then 3 is visited, then 4 is visited, and then 5 is visited. So you can think of it, this is the visit order when you are writing the DFS algorithm. Okay, so this is how your DFS depth first search will work. Now I'll just explore what is the complexity of it. Okay, so the heart of this particular algorithm is DFS visit. Now you already know that for every adjacent node DFS visit is being called. So if you check here, DFS visit is being called on every vertex. So you can think of it that the loop that is being formed here is the big O of V, because every vertex you have to visit. So V vertices you have to visit. So first complexity you can think of it of DFS visit is V. Then for the recursive call of DFS visit, it will be both the sum of the degree of the adjacency of all matrix in vertex V. So it can be written as the sum of the adjacent vertices, which will be the big O of all the edges you have used to visit it. So it will be belong to the vertex. Okay, so hence the overall complexity will become that big O of vertex plus edges. Okay, so it's very simple. Now the summary here, just what we have studied here. So DFS graph is a transversal technique that explore as far as possible along each branch before backtracking. So in the lecture you have already seen that firstly it will be try to explore each and every path by calling a function again and again. When the function in the end, when the function does not find any adjacent edge, it will be backtracked to the way it is called. Okay, so it starts as a given vertex or a node and explore as deeply as possible until it reaches a leaf node or a node with no unvisited neighbors. DFS can be implemented using a stack data structure, either using a stack, explicit stack, or by utilizing the call stack during recursive call. So this is referred to as activation records. It is often used in the applications such as maze solving, cycle detection, topological sorting, graph coloring, and finding connected components. So this is one of the things, the many applications of DFS. So DFS does not guarantee the shortest path between two nodes, as it may get trapped in cycle and take a longer route, because for this we have already another algorithms, shortest path possible, like Dijkastra and other algorithms that are there. So this is not for finding the shortest path. However, you can find shortest path in a certain conditions, but it is not always give you the shortest path. Okay, so it will use less memory as compared to breadth first search, since it explores a single branch completely before moving on to the next branch. Yes, DFS is relatively simple to implement as compared to BFS. So I'll discuss BFS and I'll tell you why it is being simple as compared to the breadth first search, because there we use Q. So Q has different complexity and other things. So the complexity of DFS we have already seen is big O to the power of V plus E, where V is the number of vertices and E is the number of edges. So DFS can be applied to both directed and undirected graph. Variations of DFS include iterative. So these are some variations of it, so you can check for it yourself. Okay, so this is how the DFS algorithm works. We have seen it, we have discussed examples. Now in the next one we'll try to explore more about the breadth first search algorithm. Okay, so thank you.